Confidence intervals for one population mean when population standard deviation is unknown. Standard normal curve and two t-curves. So our standard normal curve goes from -3 to +3 with a mean of 0, standard deviation of 1. And normally you use the standard normal curve to find your probability, but you have to know what the population standard deviation is. Since that's rare, we use something called a t-curve. The t-curve with degrees of freedom 1 is similar to the standard normal curve, but it's a little bit shorter. The t-curve with degrees of freedom 6 is a little closer to the standard normal curve. Eventually, the t-curve becomes the same size as the standard normal curve. So it's a good substitute to use when our population standard deviation is unknown. Basic properties of t-curves. Property 1. The total area under a t-curve equals 1. Property 2. A t-curve extends indefinitely both directions, approaching but never touching the horizontal axis as it does so. Property 3. A t-curve is symmetric about 0. Property 4. As the number of degrees of freedom becomes larger, t-curves look increasingly like the standard normal curve. Example. For a t-curve with degrees of freedom 16, use a t-distribution table to find the t-value t.005. First, we want to begin with just learning how to use the table for the t-distribution. When we have the notation of t.005, what they're giving us is t sub alpha, where alpha is the area to the right of t. So they have given us an area of 0.005. Going to our table, we see that our table is set up with the area to the right of our t-value. The column is t of 0.005. Degrees of freedom for our problem was 16, so we want to go to the row 16. Where the row and the column cross, give us our t-value, 2.912. t.005 equals 2.912. Example. For a t-curve with degrees of freedom 20, find the t-value having area 0.10 to its right. Draw a sketch of the t-curve with shading under the curve to the right of the t-value. We want to go to our table. Our column is t with an area of 0.10. Our degrees of freedom is 20, and where they cross is our t-value, 0.325. So t equals 1.325. Example. For a t-curve with degrees of freedom 28, find the t-value having area 0.05 to its left. So we have our curve with our t to the left of 0, and I'm shaded to the left. Since our t-distribution is symmetric, all I have to do is find the t-value for the area of 0.05 to the right and then switch the sign. So going to our table, I want to find the column for 0.05. Then I want to find the degrees of freedom of 28, where they cross 1.701. So changing my sign, t equals -1.701. Example. For a t-curve with degrees freedom 24, find the two t-values that divide the area under the curve into a middle of 0.95 area and two outside areas of 0.025. Draw a sketch of the t-curve with -t to the left of 0 and +t to the right of 0. The shading for the area under the curve is to the left of -t and to the right of +t. So I have 0.95 in the middle and 0.025 on each end. Because my table has the t-values when the area is to the right, I want to use the area of 0.025 to the right of positive t when finding my t-value on the table. Going to my table, I look for my column, the area of 0.025, which is in the middle, then my degrees of freedom, 24, and they cross at 2.064. So my t-values are negative 2.064 and positive 2.064. Studentized version of the sample mean. Suppose that a variable x of a population is normally distributed with a mean mu. Then for samples of size n, the variable t equals x bar minus mu divided by s divided by the square root of n has the t distribution with n minus 1 degrees of freedom, df. One mean t-interval procedure. Purpose: to find a confidence interval for a population mean, mu. Assumptions: 1. Simple random sample. 2. Normal population or large sample. 3. Population standard deviation unknown. One mean t-interval procedure, continued. Step 1. For a confidence level of 1 minus alpha, use the t-distribution table to find t of alpha divided by 2, with degrees freedom equal to n minus 1, where n is the sample size. Step 2. The confidence interval for mu is from x bar minus t sub alpha divided by 2 times s divided by the square root of n to x bar plus t sub alpha divided by 2 times s divided by the square root of n. Step 3. Interpret the confidence interval. Note, the confidence interval is exact for normal populations and is approximately correct for large samples from non-normal populations. Example: use the one mean t-interval procedure with the sample mean, sample size, sample standard deviation, and confidence level given below to find a confidence interval for the mean of the population from which the sample was drawn. X bar equals 23, n equals 36, s equals 4, confidence level equals 90. When we draw our t-distribution for the confidence level, we have our t-distribution with negative t and t. Here we have shaded in blue the area to the left of negative t and to the right of positive t, and shaded white is the area between negative t and positive t. That area between is our confidence level, 90% or 0.9. In order to use the table, we have to first find alpha. So alpha is 1 minus 0.9, which is 0.10. So that's the total of the blue area. To find those areas, we take alpha and divide it by 2. 0.10 divided by 2 is 0.05. 0.05 is the area to the left of negative t, and 0.05 is the area to the right of positive t. Next, we need to find our degrees of freedom. N equals 36. Our degrees of freedom are n minus 1, so df equals 35. I want to go to the table to find t sub alpha divided by 2. For this example, that equals t of 0.05. So we want to find our column, t sub 0.05, and our degrees of freedom, 35. That crosses at 1.690. So t sub 0.05 equals 1.690. Continuing, we now want to find our interval. sample mean minus t sub alpha divided by 2 times the standard deviation divided by the square root of n, to x bar plus t sub alpha divided by 2 times s divided by the square root of n. I'm going to start with the lower limit. Substituting, I have 23 minus 1.690 times 4 divided by the square root of 36. That gives us 21.873. To find the upper limit, I just want to change my minus to a plus, substituting 23 plus 0.1690 times 4 divided by the square root of 36 equals 24.127. Continuing with our example, interpret the results. The 90% confidence interval about mu is 21.873 to 24.127. Continuing with our example, obtain the margin of error by taking half the length of the confidence interval. So first I want to find my distance and divide it by 2. 24.127 minus 21.873 divided by 2 is 1.127. Make sure when you type this in the calculator that you put parentheses around the numerator of the fraction. The margin of error found by taking half the length of the confidence interval is 1.127. Continuing with our example, we want to obtain the margin of error by using the formula. E equals t sub alpha divided by 2 times s divided by the square root of n. Mean is 23, n is 36, standard deviation is 4, and t sub alpha divided by 2 equals 1.690. Substituting, E equals 1.690 times 4 divided by the square root of 36, which equals 1.127. The margin of error found by using the formula is 1.127. So whether we find our margin of error by finding the distance between the lower limit and the upper limit, then dividing by 2, or using the formula for E, we get the same result. To recap, confidence intervals for one population mean when the population standard deviation is unknown. Studentized version of the sample mean. For samples of size n, the variable t equals the sample mean minus the population mean divided by the sample standard deviation divided by the square root of the sample size has the t distribution with n-1 degrees of freedom. Basic properties of t-curves. The total area equals 1, is symmetric about 0, and as the number of degrees of freedom becomes larger, the t-curves look increasingly like the standard normal curve. One mean t-interval procedure. For the confidence level 1 minus alpha, use the t-distribution table to find t sub alpha divided by 2 with a degrees of freedom of n-1. The confidence interval for mu is the sample mean plus or minus t sub alpha divided by 2 times the sample standard deviation divided by the square root of n.